Right. Spanning tree protocol. The reason behind this protocol is loop prevention, which we learned in CCNA. Wherever there is redundant path, loop is possible. If loop occurs, what happens? Two things will happen. Number one, a broadcast storm will happen. What is broadcast storm? Storm is not simple, gentle wind. Storm is something which can destroy. Yes. A broadcast that will destroy the whole network will happen. Very dangerous layer to loop. Secondly, MAC table instability. What is that? Because you have multiple paths, the MAC address of connected devices will be learned in multiple interfaces. Let me draw and explain it. I'm taking that same old topology that we learned in CCNA. You see, you have two switches. This is switch 1 and this is switch 2. And let me call this as computer B and computer A. This computer's got IP address as well as MAC address. Let's consider this as MAC address. Now, I have a link. We learned in our CCNA that when a packet arrives, this is the frame with source MAC address AAA, destination MAC address BBB. When this packet approaches this port, let's say this is port number F01, the MAC address will be updated. F01 AAA. And now, because the switch do not know the destination, because the switch don't know BBB, switch will flood it. Now the flooding goes to all the ports except the port from where the traffic entered. Except this particular port, all the other ports will be getting that flooded traffic. This packet will be sent on every port, including this. This hits the second switch. Second switch immediately learns that AAA is connected on F010. You see, the source address is what the switches will learn. This we know. How switches learn MAC address? When a new frame comes, it checks the MAC address of the source from the packet. It checks the source MAC address in layer 2, copies the MAC address into the MAC table against the port F01. Now on switch 2, the packet is received on F010. So it learns that AAA is connected in this direction, F010 direction. As the traffic enters, it learns. What if I have two links? Then the MAC address will be learnt on two ports, which is not at all acceptable. Yeah, you cannot have like this. So we cannot have both the link active. One of the link has to be made standby by blocking. By blocking the port, we make this standby so that no traffic will be sent on the standby link. So this will not be learned by switch 2. That avoids confusion, that avoids problem. You see the problem with the loop, redundant paths, not loop. Problem with the redundant path. If you have redundant path, the MAC address learning, you will have an unstable MAC table. It's not a stable one. Which says AAA is in this port. And when it receives the copy of the same packet on the other port, it says AAA is in 11 port. Now it keeps changing. So wherever redundant path is, two things occurs. One, broadcast flooding, which we learned in the previous CCNA course. It will broadcast and it will cause flooding. It will cause loop. The flooding will reflect in loop. This is flooding. On receiving the packet, this will also flood. So the packet comes back. And then again, it will flood. So the packet goes back. Again comes back. Again goes back. Flooding is always going to cause loop if you have a redundant path. So to avoid these problems, we need a protocol to automatically block one of the port to make this link standby. If I manually shut down, then to bring it up when the link goes down, when the primary link goes down, to bring this up, it will take time. I need to log into the switch, jump into the interface, type no shutdown. That's going to take a lot of time. We need a protocol to take care of this. Spanning tree protocol does that. We saw how it does. It elects the root switch using the bridge ID. Bridge ID is nothing but the combination of priority and the MAC address. First, it checks the priority. The default priority is 32768. 32768. Because the priority is same on both the switch, what it is going to do, when the priority is same on both the switch, it is going to compare the MAC address. Comparing the MAC address, the switch with the small MAC address becomes the root switch. The root switch will have all ports forwarding. There won't be any blocking port. If this is the root switch, say for example the switch MAC address, the switch, for the whole switch there will be a MAC address. The switch MAC address, let's say it is 123. This switch MAC address is 789. So this has got the small MAC address, and this is going to be the root switch. Root switch will have ports in a forwarding state. They're called as designated forwarding port. They are designated to forward, no blocking. Now, the opposite switch needs to now decide whether to block here or here. Any one need to be blocked because the other switch is not ready to block. Switch 2 is not ready to block. Switch 1 have to block. So there is only two options, either here or here. In any one of this place, the blocking need to be done. The blocking need to be done. So what does it do? It compares the STP cost. What is the default STP cost for fast Ethernet, Geeta? Let's try. Let's check whether you remember. I know it has been a while, long, many years, many. Yes or no? What is the cost on fast Ethernet? What? No, for 100 Mbps, what is the spanning tree cost, STP cost? Sri, STP cost for 100 meg is 19. And now you see there is a tie in this cost. So what switch one will do, it will only focus on the incoming port cost. If this is F010 and this is F011, tell me on F010 what is the incoming cost that will come inside switch 1, F01, Murthy. What will be the incoming cost? 128 dot this number 10. In here it is 128.11. So Sangeeta, please tell me which one will be blocking and which one will be root port in switch 1. Very nice. Because spanning tree like small, this will be considered as a root port because it talks to the root switch, root port forwarding, and the other port will go to block. This is how the blocking port selection criteria in STP goes. We did the lab, we learned all this. It's good. Now what we are going to learn. First we have to learn the types of STP. We have the classical STP which you learned in CCNA, and we also have modified STP. You see, the classical STP spanning tree protocol that you learned is called as classical. In the document I have another word for it. That's common spanning tree. Common spanning tree. Common. This is IEEE 802.1d, which we learned in the previous CCNA class. I mentioned even this one to you. And it is called as common spanning tree protocol. What is unique in this? You will have only one instant, one copy, one instant of STP for all VLANs. Yeah, if you have 10 VLAN, for all 10 VLAN, only one spanning tree. Let me draw a diagram and explain you the drawback of this. Now you see only one spanning tree for all VLAN. And these are all trunk links because you got multiple VLANs. These are all trunk link. I have some computer here belong to VLAN 10, some computer VLAN 20, some computers VLAN 30, VLAN 10, VLAN 20, VLAN 30. All VLAN traffics now go through only this path. Only this path. Why? Because there is only one spanning tree. If that one spanning tree blocks, it is blocking for all VLANs. So what do we see here? We are losing the resource. We are not fully utilizing the resource. No optimal utilization of bandwidth available. We are wasting the bandwidth. We are wasting this resource. This will be utilized only as a backup. This path will not be used as long as this is available. Only when that goes down, say for example, this link breaks. Only after that, this block gets unblocked and now all the traffic goes through this way. So at a given point of time, you are now using only half of the resource, the other half is idle. At any given point of time, only half of the resource you are able to use. The other half is blocked. Let's say I have another switch. This is also trunk. Now this is also going to block. Now 1/3 of the resource only you are using. Very bad, no? We cannot use this switch. We cannot use this bandwidth. Our resource has been wasted here when STP blocks like this. So Cisco came up with an idea per VLAN spanning tree protocol. And this is what enabled by default on Cisco routers, or sorry, on all Cisco switches. Per VLAN spanning tree, you won't see in other vendors. By default, other vendors have got only rapid or MST, depends on the vendor. But Cisco has got something unique per VLAN spanning tree. Per VLAN, name itself says, if I have 10 VLAN, 10 spanning tree. What is the advantage? The advantage is because it is per VLAN, because for each VLAN there is going to be a separate spanning tree. I will make this as the root switch for VLAN 10, this as the root switch for VLAN 20, this as the root switch for VLAN 30. What does that mean? If I make this as a root switch for VLAN 10, this is not going to block. This will forward VLAN 10. Forward VLAN 10. Which means the other two will be blocking VLAN 10. Other two will be blocking VLAN 10. Next, when I make this switch as root switch for VLAN 20, this will forward for VLAN 20, at the same time blocking for VLAN 10. See this port? This port is blocking for VLAN 10. At the same time, it is forwarding only VLAN 20. And this is blocking for VLAN 10, but sorry, this is forwarding VLAN 10, but blocking for VLAN 20. Now, when I make this third switch as the root switch, this is forwarding for VLAN 30. At the same time, it is blocking for both VLAN 10 and 20. Blocking for VLAN 10 and 20. Forwarding for 30. And this is blocking for 10 and 30. This is 10 and 20 blocking. This is 10 and 30 blocking. And this is 20 and 30 blocking. Now you are utilizing all the resources available. We are doing manual load sharing. We only manually need to do this, right? By setting priority. How do we make these root switches? Manually, we go to the switches and set priority. We give low priority on switch 1 for VLAN 10, on switch 2 for VLAN 20, on switch 3 for VLAN 30 to achieve this. In this way, we are able to use all three paths. That's the biggest advantage of per VLAN spanning tree. This is Cisco proprietary. Per VLAN spanning tree is Cisco's idea. So there is no IEEE standard for this. The common spanning tree is IEEE 802.1d. Per VLAN spanning tree won't come under any IEEE because this is Cisco standard. Per VLAN spanning tree helps us to do manual load sharing. That is what you should remember when someone asks you about per VLAN spanning tree. This is what you have to recall and tell. Per VLAN spanning tree, because there's a separate instance of spanning tree, I can give different priority level for each VLAN so that I can do manual load sharing. Did you understand this, Murthy? Darshan? I think you're in mute. Sankita? Per VLAN spanning tree is Cisco proprietary, Cisco standard. The configuration part we will see in another class. Now we are moving on to the other type. The next one is IEEE 802.1W standard, which is nothing but rapid spanning tree protocol. IEEE 802.1W, rapid spanning tree protocol. See, as the word says, rapid This protocol is going to make faster. Faster what? Convergence. Which means the previous one that we learned is slower. Correct. So we have to now go back to the previous one and learn the previous one more time with this new point. Convergence is slower in that common spanning tree and covalent spanning. Covalent spanning tree is the modified version of common spanning tree. Covalent spanning tree is the modified version of common spanning tree. So what I'm going to say now is common for both common spanning tree and covalent spanning tree. So we will push this rapid spanning tree down. Let us talk about the common spanning tree, the covalent spanning tree convergence. Slow in convergence. Why it is slow? Because it is timer based. How long it will take? It will take approximately 50 to 60 seconds. It is slow in convergence. Let me draw a simple topology. Now, let's say this is the root switch. Once the root switch is elected, listen carefully, this is something very new point. We did not discuss this in CCNA level. Switch 1 is a root switch. Once the switches circulate the BPDU, they come to know that there is a chance of loop. Immediately this election process starts and switch 1 has become a root switch. What is root switch? I told you root switch is the centralized point of contact switch. I was telling you with the plant root as an example. The root is very important. If the root is cut off from the branch, from the tree trunk, the tree will die. So what I'm trying to say is everything comes from the root. Can branches give water without connecting to root? Branches cannot give water to leaves. Branches can only pass the water from the root to the leaf. What I'm coming to say is BPDUs are sent only by root switch. BPDUs are sent only by root switch. Other switches cannot send BPDU. In common spanning tree and in covalent spanning tree, BPDUs are sent only by root switch. No other switches are allowed to send BPDU. So the root switch BPDU is coming like this. To prevent going back, this is blocking. But the BPD is going, the other traffics won't go. BPDs are still going to maintain this block. Through BPDU, it learns that I need to block here. The BPD that is sent like this, it is going back. So this switch is blocking. What? Not the BPDU. All the user traffic. BPDs will never be blocked. BPDs are very important to maintain the block. Fine. So the commander in chief is only root switch. For example, what do I mean by commander in chief? If this link goes down, this switch cannot take a decision. It needs to wait for the root switch BPDU to time out. In this direction, the BPDU will not come because there is a disconnection. There is a break in the wire. So switch 3 will wait for the BPDU. How long it will wait? Every 2 seconds, BPDs are sent by the root switch. Now, it waits for the timeout to happen, 20 seconds. After 20 seconds, the switch realizes that something is wrong. After 20 seconds, the switch starts listening. Twenty seconds, sorry, 15 seconds. After 20 seconds, it will be in a listening state for 15 seconds. What it is listening? It is listening to the new topology change. It is listening to the new topology change. Because the root switch cannot send BPDU in the other direction, after 20 seconds, all switches will start sending BPDU. Now they have to do a rediscovery of the topology. That listening of new BPD is coming from all switches. Earlier only a root switch was sending BPD. Now all switches are sending BPD after timeout. So it is listening for 15 seconds and then it will start learning MAC addresses on the new path. That learning will be 15 seconds. And then it moves that mode to forwarding. If you see to make a blocking port to forwarding port, it has taken 30 plus 20, 50 seconds. That is what I wrote here, 50 to 60 seconds. It depends on the size of the topology. Slow in convergence. I'll show you this delay and all in lab when we do lab. Today we are learning the different types of spanning tree, theoretically. Now next class we will see the lab of these things that we are learning. So here, to unblock a port, when this link goes down, all traffic which was going this path now should go via this path. To allow via this path, this need to be unblocked. To unblock only it took what? 50 seconds. In 50-second, big network will be sending thousands of packets. All thousands of packets will be dropped in that 50 second. This is the problem with the common spanning tree or prevalent spanning tree. They are slow in convergence. They are timer based. I told you timer based. The common spanning tree is timer based. This is what the timer is. 20 seconds of wait time, and timeout happens after wait, and then 15 seconds of listening and 15 seconds of learning. Timer based. When a link goes down, when the primary path link goes down, to bring the alternate path from standby mode to active mode, it takes 50 seconds. We don't have this delay in rapid spanning tree protocol. We don't have this delay in rapid spanning tree protocol. The reason is, in rapid spanning tree protocol, every switches will send BPDUs. Every switch will send BPDUs. Every switch through this BPDU learn who is responsible if something goes wrong with the primary part. Every switches will know where the block is. Every switch will know which is the alternate path. If something goes wrong with the primary path, they immediately swap the traffic through the alternate path. Immediately they swap because they know. Very first time only they listen and they learn. They don't learn every time. When a link goes down, say for example the same topology, I'm drawing same topology. Switch 1, switch 2, switch 3. This is the root switch. And there is a block here. The difference is here every switch is sending BPD. This switch is saying, hey, I am blocking on this port. And this switch now knows who is responsible for the block. Switch 2 also knows that which path is the alternate path. So as soon as this link goes down, get broken, immediately the switch, what it will do, all the traffic that was earlier going this way, it will swap to this way. Just the database will be shifted, that's all. The MAC addresses that which were going on the upper path now will be shifted to the down path. So the traffic will go just like that. It will take like 2 to 3 seconds only. Why 2 to 3 seconds? Because the BPDs are sent how often? BPD hellos are sent every 2 seconds. So in 2 to 3 seconds, this convergence will happen. This will be unblocked. Every switch knows the whole topology, and every switch knows if a link goes down, how the packet need to be shifted, where it need to be shifted. So immediately that happens. As soon as the BPDU stops coming, as soon as this link goes down, as soon as the BPDU between these two stops going, when the link goes down, they immediately take the decision to forward the traffic this way instead of forwarding via this way, just swapping. So this port cannot be called as a blocking port. It is called as adjacent port. Sorry, alternate port. And everyone knows that this is an alternate port. Switch 2 knows that switch 3 has got the alternate path, alternate port. Switch 1 also knows that switch 3 has got the alternate port. Every switch sends BPDU. Every switch sends the notification, the status. So in this, you see, they listen and then they forward. No learning. Only in the beginning they will learn. And this listening is not a timer based. In the previous case, listening is 15 seconds. Even if there is nothing to listen, it needs to wait for 15 seconds, hoping that there may be something new coming from somewhere. Listening 15 seconds, learning 15 seconds, it's timer based. But here, this is not a timer based. As soon as the link goes down, immediately this guy sends a topology notification. This guy immediately turns this as forwarding. Every switch can take a decision here. Whereas in the previous case, everything was depending on root switch. Root switch should time out, and then all the switches will start sending BPDU and start listening, and then they will start learning the new topology, and then only they forward. Here, they learn right in the beginning itself, and every switch sends BPDU, so they keep learning. Everyone knows where the alternate port is. And if something goes on with the primary path, immediately the alternate path will be turned to forwarding as soon as the notification comes from switch 1 or switch 2. If any one of the switch sends the notification in the BPD, that's enough. Switch 3 can immediately unblock. No timeout, nothing. This makes this protocol rapid. Now, this rapid spanning tree in Cisco is coming as a combo with per VLAN spanning tree. Rapid spanning tree comes in conjunction with per VLAN, meaning if you enable rapid spanning tree, it is for individual VLANs. Meaning, if you enable rapid spanning tree, it is not one rapid spanning tree for all VLANs. It is not only one rapid spanning tree for all VLANs. For each VLAN, separate rapid spanning tree. You see, you no need to say, I want rapid per VLAN span. No, you don't need to say that. When you simply enable rapid spanning tree, this gets enabled in Cisco, but not in every vendor. In Cisco, it is like that. Cisco has designed their device like that. I've seen Huawei and other devices. Rapid spanning tree is separate. With that, you can attach this per VLAN spanning tree. But per VLAN spanning tree is Cisco, no? Yeah. But for this rapid spanning tree, there is IEEE version, a modified version. No. It's modified version, but it's not IEEE. Anyway, so what I'm trying to say is in Cisco, this is what you need to remember. When you enable rapid spanning tree, it is not only one rapid spanning tree, it is for each VLAN one rapid spanning tree. 10 VLANs, 10 rapid spanning tree. This rapid spanning tree is faster because it is faster. The CPU utilization will also be high than common spanning tree. Now, when I have 100 VLANs, then if I run 100 rapid spanning tree, then CPU is going to be very highly consumed. Heavy consumption of CPU. High consumption of CPU. So if you feel like that, you have an option. That is the next type. If you say it's too heavy, too much of CPU, because rapid spanning tree runs for every single VLAN separate instance, CPU is very high. If you find that, or if you feel like that, then you have an option called MST. MST is nothing but multiple VLANs mapped to single instance. For example, I can say, though I have 100 VLANs in my switch, I say copy 1 will run VLAN 1 to 50. The other copy number 2, MST uses rapid spanning tree. Copy number 2 of rapid spanning tree will be responsible for VLAN 51 to 100. So you can map like this many VLANs to one instant. You can map multiple VLAN to a single instant manually. When you simply enable MST, and when you don't do this mapping, there will be an instant number 0 to which all VLANs will be mapped. This is default. When you enable MST, and when you don't map grouped VLANs, the grouped VLANs to instant, by default, all VLANs will be a member of instance 0. This is not given by you, this is default. When you enable MST, this gets enabled. But you can do like this, so that when you have multiple spanning tree, you can do load sharing as I showed you earlier. You can set different priority on different switch and we can have load sharing. That is why you need multiple instances, right? So we have common spanning tree. 1 minute. This is called as IEEE 802.1s standard. Okay. So we have common spanning tree, which is only single spanning tree for all VLANs, and then per VLAN spanning tree, which is Cisco proprietary, runs a dedicated instance for each VLAN, and then rapid spanning tree, IEEE 802.1w. This is fast in convergence, but Cisco uses the modified version, which we called as rapid spanning tree per VLAN spanning tree plus, meaning when you enable rapid spanning tree, automatically it is going to run separate instance for each VLAN. In the other vendors, this is what they do. Only one STP, but fast STP. Whereas in Cisco by default, when you enable RSTP, it's RSTP PVSTP plus. This is simply PVSTP. This is PVSTP plus, meaning it is combined with rapid. But the problem is more CPU intense. So you have grouping of VLANs and mapping into dedicated instant. We call it as multiple VLAN spanning tree protocol, which is IEEE 802.1s. And we also saw how they work. The normal spanning tree, how they work, and then rapid spanning tree, how they work. I have those differences here down. You see? The normal spanning tree is ID 1D, rapid spanning tree is 1W. This is timer based, 30 to 50 seconds. This is just 2 to 3 seconds only. Right? This is fast in convergence, not just the loop prevention, it is also fast. And here, the BPDs are generated only by the root switch, whereas here, every switch sends the BPDU every 2 seconds. And here you have listening, learning, and then forwarding from blocking. From blocking to bring into forwarding, you need to go under 5 stages. Whereas here, it is discarding, learning, and forwarding. Discarding is nothing but the alternate. Port will be in discarding mode. Yeah, here it is, alternate port. Right, so you don't have 5 states, you have only 3 states. It is in a discard mode. As soon as the new BPDU comes, it starts learning and forwarding. Boom, that's it. All right, now this normal spanning tree is compatible with, correct. The older STPs. This turbulent spanning, this rapid spanning tree is compatible with normal STP. IEEE 802.1d is slow. This is faster, immediate, 2 to 3 seconds. In Cisco switches, it is per VLAN and per VLAN rapid. No, so same thing here. Explain. In IEEE 802.1d, you have this 5 stages, whereas here it is only 3 stages. And this is not a timer based, that is timer based. Right? And also we saw MST. MST is nothing but multiple VLANs can be mapped to a single instance. See, group of VLANs. Oh. Group of VLANs can be mapped to the separate instance. You can decide how many spanning tree can run. Right, more about this is coming in our next class. We'll be doing a little more theory and then we'll get into the lab. I would like to hear from you some questions now. Do you have any questions?